Section 9.4, hypothesis testing for means. Okay, so we have already covered hypothesis testing for proportions back in chapter 7. So again, the basic structure of this is not going to change. The 4 steps are not going to change. We are just now changing where we go in StatCrunch in order to have this work appropriately for means. So I'm not going to go through the 4 steps again, though we've already talked about those. We're just going to kind of jump right into one slowly, but jump into one example where we're talking about means now. So it says McDonald's advertises that its ice cream cones have a mean weight. So this is how we know we're using just a slightly different place in StatCrunch now. The mean weight of 3.2 ounces. But a human actually starts and stops that machine, so we should expect that they're not all going to weigh exactly 3.2 ounces. So if we weighed all of the cones at a particular store, would the mean be 3.2 ounces, as the company claims? So they should at least average out to what the company is claiming is the idea. Let's say we sample 50 cones and we calculate the sample mean. So just as a reminder, sample mean symbol is X bar to be 3.68 ounces and the standard deviation S to be 0.3701 of an ounce. Do these observations support the claim that the mean weight is 3.2 ounces? We're going to perform a hypothesis test, and we're going to use that standard significance level of 0.05. Okay, so our first step is to actually write our hypotheses. So our null and our alternative in this case. Difference in symbolism now. Because we're talking about a mean, we're going to be hypothesizing about the population mean, which is symboled with mu. Those were p's in chapter 8, p's for proportion, but again, we're now in mean world, so now we're using mu. So our null would be the very boring stance of everything is as it should be. The mean weight is indeed 3.2 ounces. And in this case, it doesn't seem that we're really concerned about whether it would be more or less. We're just concerned about, is it something else? Is it something different from this? So my alternate would just be simply that the mean weight is not 3.2. Because of that, because of this being the not equal to symbol, this would be an example of a two-sided hypothesis. Okay, so there we've written our hypothesis. So now we need to prepare. In the preparation step, we remind ourselves of what alpha value we're using. So we're using 0.05. This is the probability of making a mistake and failing, and rejecting the null when it's actually true. We're going to use the one sample t-test because we're talking about a mean, and we're going to use that t statistic. So again, instead of calculating a z like we did back in chapter 8, we're going to now calculate a t value. It still tells us the same thing. It tells us how far away what we observed is from the mean. Values far from 0 tend to discredit the null. And why? Well, it's the farther out you go, the smaller the p-value gets, and that's the less likely it is that the result was simply due to chance. So again, even though we're using the t distribution now instead of the z, they look basically the same. The only difference is this one has a little bit more area out under the tails. Here's your center. The farther out that t value gets, then the less area there is to be shaded under the tail, and the less likely it is that whatever you saw was just due to random chance, and the more likely it is that something is really fishy going on here. Okay, so the conditions that we have to make sure we hit are a random sample with independence and a large sample. Again, this is the one we normally do, is that 25 or larger that we have to check off for our sample size. Then we are going to compute and compare. Oh, wait, so we need to make sure. Did we hit the 25 or larger? How many cones did they sample? Let's go back. They sampled 50 cones. So we are good to go. We can check this off. Yes, because 50 is greater than 25. So we can go in and we can use StatCrunch to find these values now. I'm going to go ahead and do that. Reminding myself the information we had. We're going to have to sub this in. We're going to have to sub in way up here this information, because that was the sample mean and this was the sample standard deviation. Okay, so we can go back over to our StatCrunch. Again, we're going to go to T-Stats this time with summary, one sample with a summary again. The sample mean we had was 3.68 with a standard deviation of 0.3701. The sample size was 50. We are performing a hypothesis test, so we want to keep it clicked on that. But remember, you always have to change your hypotheses here. So it's in this case that it would still be equal to 3.2. That would be our null. And we decided on the two-sided alternate hypothesis, so we're actually okay to leave that one as not equal to. And we can go ahead and compute after that. So our t-stat looks like it's 9.17, and our p-value is very tiny. Go down here to record that. So it was 9.17, and the p was simply less than 0.0001. And that's the different part. The different part is where you go in StatCrunch and the fact that we're now getting a t value instead of a z value back. But how you interpret this is exactly the same. So we're going to take that p value and compare it with alpha. So since in this case p is very small, it's certainly less than alpha, which we used as 0.05 in this case. So when p is low, the null must go. So because we have such a low p, we're going to reject the null hypothesis, and we're going to interpret that then. So it seems like in this case, our null was that the mean weight is 3.2. We're rejecting that idea. We're instead going with the idea that the mean weight of cones at this particular McDonald's anyway is not 3.2 ounces. And that's as far as we can go there. We can't claim that it is more or that it is less. All we were testing was, is it something different? And we just found that we have enough evidence to say, yeah, it is. So remember, again, when we're hypothesizing about means, we will always use the t-stat area in StatCrunch.